Hi everyone, how are you doing? I hope you are all doing well. My lovely pupils, today I am going to review another subject, page 154. Subject types of stars. On a clear dark night, you can see that although most stars are white, some are blue, and others look red. What causes the different colors of stars? What causes? The color of a star is a clue to its surface temperature. Blue stars have the hottest surface temperature, but the red stars have the coolest. Red stars have the coolest, but blue stars have the hottest surface temperature. This point very important. My pupils try to pay attention to these points. Blue stars have the hottest surface temperature, but red stars have the coolest. Do you remember this question? What is the relationship between the color of a star and its surface temperature? The answer of this question is that blue stars have the hottest surface temperature, but red stars have the coolest. Astronomers use surface temperatures and absolute magnitudes to classify stars. In the early 1900s, scientists classified stars. They used a diagram similar to the one above. The diagram shows the relationship between size, magnitude, temperature, and color. Magnitude and temperature. Magnitude and temperature and color. This note very important, my pupils. Please try to pay attention to this note. Scientists classify stars based on color, size, absolute magnitude, and temperature. The diagram shows relationship between color, size, magnitude, and temperature of stars. The absolute magnitudes of stars are plotted from bottom to top. If you go higher, the stars will be brighter. The stars will be brighter. But the brightest stars are the top. Brightest star at the top. But the surface temperatures of stars are plotted from right to left. The hottest stars are on the left. The hottest stars are on the left. If you go left, the stars get hotter. If you go left, half stars get hotter. Blue stars have hottest, but red stars have coolest. Very, very important. Please try to pay attention to these pointers. Red stars have the coolest, but blue stars have the hottest. Red giant is a very old star. Try to pay attention to this point. Red giant is a very old star. Red giant, it is a red color because it is a coolest star. Supergiant, it is a coolest star. It is a red color. But the sun Sun, it is yellow color, warmer than red giant and supergiant. White dwarf, it is the end cycle of the sun. White dwarf, it is blue color. It is blue color because it is hottest stars. Hottest stars. Please watch this video about types of stars.
It's Professor Dave. Let's check out some stars.
He knows a lot about the science stuff. Professor Dave explains.
Now that we are about 1 billion years into the history of the universe, we can see a panorama of stars swirling around in galaxies, which have in turn collected stars. So what happened next? The answer to this question will require that we learn more about stars and their characteristics, which determine the way we categorize them. So let's learn the basics about this system now. When we first started to observe stars in telescopes, we divided them into color classes: white, yellow, red, and deep red. This was later refined, and each color was broken up into letters: A to D for white, E to L for yellow, M and N for red. Later, it was realized that things made more sense if stars were categorized by surface temperature. But this letter system was retained because all the work to classify stars had already been done. So from hottest at around 25,000 Kelvin to coolest at around 3,500 Kelvin, we now have O, B, A, F, G, K, and M stars, a classification system called the Harvard system, which was developed by early astronomer Annie Jump Cannon. This sequence of letters is rather unintuitive, but to remember the order, we can use the following mnemonic. Oh, be a fine girl, kiss me. Feel free to replace girl with guy, depending on your persuasion. Or if you find the whole thing terribly sexist, just make up your own, such as, omniscient beings are firing gigantic knowledge missiles. As we can't stick a thermometer into a star to see how hot it is, this classification, based on temperature, is actually derived from Wien's law regarding black body radiation, which we saw in the Modern Physics series, as well as other types of data, like emission spectra. We analyze the light we receive from a star and correlate it with a particular temperature, as well as with specific elements, just like when we learned about the Bohr model in general chemistry. The hotter the star, the more of the hydrogen and helium nuclei that have been stripped of their electrons, forming the phase of matter known as plasma. The hottest stars, O stars, show very little hydrogen because most of the hydrogen is without an electron and thus can't absorb and emit light. Helium is still able to retain one or both electrons, and thus we do see emission correlating with helium. Cooling down a little with A stars, suddenly hydrogen can hold on to an electron, so the spectrum changes. Getting cooler still, some bands show up that correspond with metals, like calcium. So the convention is derived from temperature, but this happens to correlate with color and size as well. Hotter objects, like O and B stars, are blue, and cooler objects, like K and M stars, are red. Also, hotter stars tend to be larger and burn brighter, with the additional heat resulting from the fact that so much more fuel is being burned. All of this data regarding temperature and luminosity, as well as indirect information on mass and radius, can be represented on something called a Hertzsprung-Russell diagram, or an HR diagram for short. In this diagram, the horizontal axis shows temperature decreasing to the right, and the vertical axis shows luminosity, or the amount of energy emitted by a particular star per unit time, increasing going up. We can see that the majority of stars fall on a continuous curve, which we call main sequence stars. 90% of all stars follow this trend, including our own sun, which is part of this yellow region here. Some stars, like red giants, are very cool yet luminous, while others, like white dwarfs, are very hot yet dim. but the majority belong to this main sequence. Even though this diagram lists only temperature and luminosity, we can infer many things about other variables. Larger stars are always more luminous, as more surface area means more energy emitted. We can also see color clearly correlating with temperature as we move from left to right. Size is also represented, with main sequence stars decreasing in size from left to right, but with red giants and white dwarfs as the mass-luminosity relationship that we just described. It explains why the blue stars in this corner of the main sequence burn brightest, getting dimmer as we go towards the smaller red stars. This has to do with the fact that the gravity crushing the star inwards increases exponentially with its radius, so larger stars have to generate much more outward pressure to prevent collapse. So that's some basic information about all the stars in the universe. Remember, for the main sequence, blue stars are big and hot and bright, up to about 100 to 200 solar masses, or 1 to 200 times the mass of our Sun. Red stars are small and cool and dim, down to around 1/10 the mass of our Sun. Yellow are in between. These are about the size of our Sun. Then beyond main sequence stars, there are red giants and there are white dwarfs. Those are the three main classes of stars. Most of the stars that have existed in the past, and most of the stars that exist today, fall into one of these categories. But they are not static. They will move between these categories over time. So how does this happen? And how is it that stars eventually die? There is a lot to discuss here, so let's move forward and learn about the lifetime of stars.
Okay, my students, today I finished the lecture. See you next lesson. Goodbye.